Okay, we're getting down to the last chapters here. So here we're going to be looking at the two-sample problem that typically emerges. And so what we're trying to do here is we're going to be trying to look at the difference. If we have large independent samples, we're going to try to determine whether there is a statistically significant difference in the means of those two different populations, and we're going to also develop a confidence interval for that mean. So you see that that's really our goal here in this chapter. You can obviously see that some of the applications of this would be is that wanting to see if one population that receives a particular pharmaceutical drug or something, if they have a mean score that's significantly different than another population that does not. We could think of other kinds of things here. And that also then what we're also going to do here is, again, look at how to construct those hypotheses testings for those two different means. Okay, so let's start. So, what we would do here is if we have two populations, and each sample of those populations is a large independent sample, how would we know they're large enough? Well, they're bigger than 30, right? The sample size is bigger than 30. Then what we want to do is look at the difference in those means. So here you can see that we're subtracting the two mean scores. And that what we're trying to do is see, is there a difference between those two mean scores? Is this a non-zero number? And then if it is a non-zero number, what kind of statistically valid educated guesses can we make about it? And you can see this here. So again, here's the idea. Two independent populations, two samples of those populations, and the question being, what does the mean values look like? And what's the standard deviation of those, the distribution of the sample? And is there a difference between the two? Or are these mean values not statistically different from one another? So, what we would need to do here is we would need to start to construct a confidence interval between the two. Whoa, this equation certainly did not translate well into... sorry, let me get it here. Did not translate well, so let me rewrite it here for us. So our value here would be our difference in the means, right? So here's our difference in the mean values of the two samples, plus or minus, because we're developing a confidence interval. So we're doing our z-value here. And putting that together with our variation and the size of our sample size here. So let's start to apply this, okay, with this set. Again, provided that each sample size is large enough. Well, then the first thing we need to do here is let's start to apply this. What if we have this following data? So we have two samples that are each large enough, 174 and 355. We have mean values provided of 3.51 and 3.24. And we have a variation of 0.51 and 0.52. Now we can obviously see that these mean values are different, but we need to determine what the 99% confidence interval will be for that difference. So let's start to set that up. And none of this is really coming out here, but don't worry, I'll rewrite this out here. Okay, so let's first find out what that difference is. Well, that one is simple. What's the difference between the mean scores? That would just be our 3.51 minus our 3.24. So we've got, we're going to start out here with a difference of 0.27. Okay, so now we're constructing a 99% confidence interval. That z-score is 2.575. We get that from the z tables that are in the back of the book or in the appendices for Flatworld. At the 99% level, you can see that each of these would be divided by 2, because each tail would be 0.5%. So that z-score is 2.575. So taking them by difference of the means, 3.51 minus the, it looks to be a typo here, not 2.24, but 3.24. So 3.51 minus 3.24, that gets you also a difference again of 0.27. Plus or minus 2.575 of the square root of the 0.51 squared over 174. I'm just going to rewrite this part here. Plus 0.52 squared over 355. Times 2.575 times this. So, as long as your calculator is operating properly, and I did check my work before I'm creating this lecture, it does work out to be 0.12. So now we're going to take our mean value and then add or subtract 0.12 to get this now 99% confidence interval for the population means. Okay. Now, once we can do that kind of work, what we're probably going to do, or probably what you're going to want to do, is be able to calculate these numbers with hypotheses stated. And we would have a null and an alternative hypothesis. These are going to be expressed, these hypotheses are going to be expressed as the difference in the means. And we generally would start with a null hypothesis, where the null hypothesis, or h subscript 0, or null, is equal to the difference of the means equaling some value. So that's that pre-specified number here is d subscript 0. The alternative hypothesis, depending on what your research question is either you're going to be looking for there to be a left-tailed difference, a right-tailed difference, or some two-tailed difference. It's all going to depend on what you're trying to measure here, what kind of phenomenon you think exists, right? So if we want to say that taking some prescription drug reduces some bad disease, then we're probably going to look for some sort of right-tailed hypothesis that we're trying to accept, because we want the difference in the means. We want the difference in the means to be such that for the um, new population, that the new population has been positively affected by taking this pharmaceutical drug and is less likely to get the disease. Alternatively, if if we were looking at the effect of drinking caffeine on a person able to stay up longer, well, we were expecting that the person is going to be able to stay up longer, so now we would see a left-tailed error, and that would, or not a left-tailed error, but a left-tailed hypothesis that we accept, such that taking caffeine causes you to stay awake longer. And then the third alternative hypothesis could just be that they're different. That we have some difference that lies outside of, that there's a statistically significant difference in the two means. And this didn't come out exactly well here, so let's rewrite this here. So what we're saying here is that the standardized test statistic then will be the following, as we're trying to solve this. So let's, one of the things that we'll try to accomplish here then at this point would be that we calculate again these z statistics to ensure to be able to test whether we have a right-tailed error, a left-tailed error, or that they're just, again, different from each other. And so where does that take us here? Well, none of these equations want to come out here. Okay, let me pause this. I'm going to try to reopen this in PowerPoint. Okay, so when we look at constructing then the confidence interval, again, our structure here would be our difference of our means right here, plus or minus. Now we're going to do it for the t statistic instead of the z statistic. So remember, when we're when we're using the t statistic, the difference here is going to be whether we're dealing with a large independent sample or a smaller independent sample. The t statistic allows us to deal with that smaller independent sample. So with a t statistic, we do need to deal with the degrees of freedom. Remember that that's going to be n minus 1. So now our variance, to calculate the variance that we're going to have to square, requires us to subtract 1 from each of the sample sizes to get our degrees of freedom. And then we're going to need that total degrees of freedom, which would just be summing up the sample sizes and subtracting 2. We're going to need that when we're looking at the t-statistic table in the back of the book. And what that gives us here is a null hypothesis that we can test for, as well as an alternative hypothesis. Here we need to calculate that t-statistic itself and subtract out what our designated value is from our null hypothesis. But again, we just follow the math here, the math which was stated already here. We just follow here, except now we're doing it for our hypothesis test, where we're subtracting the value that's from the null hypothesis. And to construct then the confidence interval of the difference, for now, again, small independent samples rather than larger samples, we can see that the construction of the confidence interval isn't that much different in construction, where our difference of the mean here is d bar, plus or minus then our t statistic, depending on what value we're looking for. We're going to have to get that t statistic again, keeping in mind that we need our degrees of freedom, which is n minus 1. And then we're going to have our standard deviation divided by the square root of the sample size. But hopefully this will make a little bit more sense as we're going through the practice questions as well. Or not the practice questions, as I go through the homeworks as well. Nothing different here. The, what we do for the testing the alternative hypothesis as opposed to the accepting the null hypothesis, no difference here compared to what we did for the large independent samples. So no difference. Sometimes it's going to be appropriate to have a left-tailed test, sometimes appropriate to have a right-tailed test, or sometimes you just care that there's a difference and it doesn't matter on which side. The pair differences, the paired samples rather than independent samples, doesn't really change things around that much. When we're dealing with paired samples, remember that the an independent sample would mean that the sample is independent, that it's not influenced by the other sample set. For the paired sample, there is obviously a relationship between the two. The n here is now referring to the pairs. Oh, yeah. Oh, no, I'm good. The n here is referring to the pairs. And really the only difference that the only kind of difference we see here is that for the paired samples that we're really just primarily focusing on this with a t distribution rather than a z statistic. So, what do we see in the comparison here, right? In the comparison, what we see is that, with the paired samples, if we start to instead look at, rather than small independent samples, look at large independent samples, and we look at the proportions now instead, right? Instead of looking at means, now we could test the frequency of certain events happening. And looking at these two large independent samples in terms of their proportions, it's not going to be, it really should be in some sense kind of just a repeat of what we've looked at in previous chapters here. Now we're just testing the difference in the proportions using a z statistic because these are large samples. And then essentially we're just plugging in the data here to determine whether there is a statistically significant difference in the proportions, and then to construct a confidence interval of those proportions. Same as before, we're going to have sometimes where we're just interested in whether there is a difference or not. So sometimes we'll have a two-tailed test. Otherwise, we'll be concerned with a left-tailed or right-tailed test, depending on what we're looking at, what we're concerned about. To calculate that z statistic, we could take our difference of the proportions. We could take our difference of the proportions and subtract what's in our null hypothesis. And then in the denominator, determine the extent to which our proportions, adding up our proportions together. The final part to this would be looking at this in terms of our error value, and looking at our confidence interval in those errors. So one of the things that we do is we try to find out for a specified error level that we want in our confidence interval, how large of a sample size do we need to get to that point. So we've done this before. This is no different. It's just instead we are dealing with independent samples rather than the population as a whole. And putting that together with, again, finding our minimum sample size for the difference in the means for the paired samples as opposed to our independent samples. And then finally putting that together with, once we've been able to calculate our sample sizes with 2 independent samples versus paired samples, we can look at the we can calculate the difference in the proportion of the populations with some error level. And so that's our estimating the difference between the 2 proportions. Okay, so what do we what's the purpose then, I guess, of what we've just done? Is that for the most part what we've done is we've focused, at least as a preview here of these lectures, of looking at these proportion samples and applying them to paired samples versus small independent samples versus large independent samples. And doing the same sets of things, which is constructing minimum sample sizes, constructing the error levels, constructing alternative and null hypotheses as either right-sided tests, left-sided tests, or just that they are different themselves. And then finally, doing that all for, again, small independent samples, large independent samples, and paired samples. Okay. Hopefully, again, as I try to do here, the lecture that I'm providing you here is just kind of more of a preview. I focus a bit more on the application, which is why then this will be followed up with a video that talks you through how to solve the homework questions and basically apply the material from this chapter.